Hello everyone, my name is Martin Albrecht. I'm a principal research scientist here at Sandbox, and today I want to talk to you why it's hard to build performance enhancing technologies from lattices. As you may know, lattices are one of the primary enablers for post-quantum cryptography. In particular, they give us what we call KEMs in cryptography, which are ways of establishing keys for encryption over the internet. And as you may also know, lattices are the key enabler for something called fully homomorphic encryption, right? Which enables you to compute on encrypted data. And given that lattices seem to be so good at basic tasks, establishing keys, and so good at really kind of like complex tasks, like computing on encrypted data, it is maybe a little bit confusing why it would be hard to kind of lift all of these technologies that we have in a pre-quantum world to a post-quantum setting. And I want to talk you a little bit through of like what the difficulties are that we're facing them and how we're tackling them. And I'm going to use oblivious PRFs as the running example. And don't worry if you don't know what an oblivious PRF is. That's one of the first things I will explain to you. All right, let's get started. So, as I said, I will start with oblivious PRFs, then I will walk you through the learning with errors problem, which is one of the fundamental hard problems on lattices, and contrast that with the Diffie-Hellman problem, talk you through the troubles that we have, and then wrap up. Okay, so a verifiable oblivious PRF is essentially a function where one party, which we like to call the client, submits an input, which we might call a message, and the server submits a key. And then we compute this function under the key K on the message to output some, we might call a ciphertext or some output C, and we send that to the client. And to the server, we send nothing. That's what this kind of funny symbol, which we call bot, means. Right, so what this is the client contributes a message, the server contributes a key, and at the end, the client walks away with an evaluation of this function f under this key, but the server doesn't learn the input of the client, and the client doesn't learn anything about the key of the server. And we call this thing verifiable if the client can in addition be assured that definitely this function was evaluated, not something else, right? So it knows that the relationship of C to M and K holds. And a PRF is a pseudorandom function, and you can think of it as a function where the outputs look random if you pick a random key. Okay, so these are like some cryptographic primitive, and you might wonder why you should care about them. And it turns out oblivious PRFs or OPRFs have a variety of applications. I'm gonna just highlight one here, which is called privacy pass, which is a thing that Cloudflare initially pioneered. And so if you are surfing the internet and you're trying to surf websites that are protected behind Cloudflare's proxies, you might occasionally be asked to solve some CAPTCHAs to prove that you're not a bot, right? And in particular, if you're accessing the web through Tor, then that is quite common, right? Because of a lot of bots are run through Tor because people want to hide their activities. Now, and that gets kind of very annoying very quickly, right? Every website you open, you have to solve a CAPTCHA. So what you would like to do is solve a CAPTCHA and that to prove that you're human, that you're not a bot, and then you move on with your life, and then you browse the web. The problem with that is that, of course, that means now you're identifiable, right? If you prove that you're human, then like this proof needs to somehow arrive with Cloudflare, and then Cloudflare could piece together which websites you're visiting. And we don't want that. So what you do instead is something called privacy pass, where you solve the CAPTCHA. And then once you solve the CAPTCHA, you essentially send a bunch of these messages M to Cloudflare. Cloudflare will evaluate kind of this function fk and OPRF, and you get a bunch of answers C back. And then each time you visit a website, you send a pair of M and C to Cloudflare, and it can check that these are indeed kind of like previously you have been evaluating this function fk. But it cannot tell when you did that. So who of the many users who evaluated this function you are. So it just knows you have previously proven that you're human, you're not a bot, but it doesn't know when you did that and how that relates to any other website. Okay, so that is one of the many applications. It is also used in Signal, for example. It is really quite widely used. And one of the reasons why we use OPRFs so much is because they're very efficient in a pre-quantum setting. So here I'm assuming that you are vaguely familiar with Diffie-Hellman, And so the construction, the way it goes, is that we take our input, which I now renamed x, I apologize for that, and we kind of like running this through a hash function, which somehow ends up in the group, and then we're multiplying this by g to the r, where r is like some exponent that the client picks, and g is the generator of the group, and then we call the output of that cx, and then we submit that to the server. The server will take that to the power of k, which is its key, and it will also return g to the k, where g again is the generator, and it will return both of these elements. And the client will then simply divide the x, which it had received from the server, by c to the r. Remember, the client knows r. And then if you follow the arithmetic through, what you get is h of x to the power of k, which is our PRF evaluation. And this thing is correct because effectively what we're doing is we're multiplying by g to the rk, and divide by g to the rk again. So these things cancel out and we are stuck with h of xk. So this is a very kind of simple and natural construction. It is very efficient, so that's why people like to rely on it in their protocol design. Okay, so now let's talk about the post-quantum setting. So all of this is nice and well, but we all know that a Diffie-Hellman problem isn't hard on a quantum computer. So we are moving on, and we kind of like taking out the plumbing of the internet and replacing it with post-quantum solutions. And for example, amongst the NIST standards, right, for post-quantum cryptography, 3 out of 5 are based on lattices, right? Kyber, dilithium, and Falcon. And in and these are for digital signatures and for KEMs, which are key establishing mechanisms. What it stands for, key encapsulation mechanism, but like it is used to establish a shared key between two parties. And so these would be considered like the lowest level primitives that we need in a public key setting. Right, and then Kyber is, I put it on the slide here, Kyber is bigger than elliptic curve cryptography, it's significantly bigger. However, it is faster, right? So, it is fairly, as far as lattices or post-quantum schemes in general are concerned, it is fairly efficient. So lattices seem to be good at the low-level public key cryptography, but they're also quite expressive and useful for really the top of the stack. So I had already mentioned fully homomorphic encryption, which enables you to compute and encrypt the data. You can also build something or some candidates. There are some ideas for building indistinguishability obfuscation from it. That means encrypting programs and running them on clear text inputs and outputs. You can do functional encryptions where you can decrypt to any function. So there's a lot of very expressive things that we know how to build from lattices. So it might appear a little bit confusing that then why can't we do things like OPRFs, which seem to be not much more difficult than key establishment. So let me kind of walk you a little bit through what I mean when I say LWE, which is the problem on which Kyber is based. And so what the LWE problem is that we're given a random matrix, mod Q, of dimensions m by n. You can think of it as a square matrix for now. And then we have some vector C. And then we're asking the question, is the vector C arrived at by multiplying A by some S, which is some secret, and then we're adding some small error term to it, or is C simply sampled uniform at random, right? So you're asking the question, is C formed this way, or is C uniformly random? And you can also formulate a search version of this problem, which essentially asks, give me S, given that C is computed this way. And then you can write down this equation, you can write down the coefficients, in the matrix and in the vectors. And then what you end up with is something what is a little bit annoying. You need roughly n squared storage, right? So you have the rows and the columns, they're each dimension n. And then to multiply, you also have a quadratic cost. You can do a little bit better by essentially replacing the matrix that we've just seen with something more structured. So here the first column is again random, but then all subsequent columns are obtained by shifting the previous column and flipping a sign, right? And so I'm flipping from column 0 to column 1, and I'm flipping from column 1 to column 2, and so on. And turns out if you do that, then you now have storage n, so it's only linear in n, and the computation can actually be done in n log n, which is again smaller than n squared. And the reason why computation can be done more efficiently now, because there was actually a convoluted way of writing polynomial multiplication modulo x to the n plus 1. And this is what we call the ring LWE, or more properly, the polynomial LWE problem. right? That was introduced around 2009. And so the way I'm gonna write this, I'm gonna write AI, which I denote as a ring element in this polynomial quotient ring. I have an element S, and then I have an element EI, right? And then the AI and the EI shares like these can change. I can ask for many of these AI-CI pairs, but the S will always remain the same. And also what I'm doing is I highlight in orange elements that are small, right? That have small norm, right? So the error term initially was small, but it turns out you can also have the S coming from the small. So really think of small of like, each coefficient is between -4 and 4. That is a pretty good kind of mental bridge here. All right, so if we have this notation, then there's actually almost a dictionary, right? So you can take your construction in a Diffie-Hellman world and you can turn that into, in some sense, mechanically, into something that lives in ring LWE land, right? So you have a generator that for us would be this kind of random element A, and then g to the x becomes effectively A times S plus E. And then, as you might know, in a Diffie-Hellman world, when I multiply g to the x by g to the y, that is the same as adding the exponents, so computing g to the x plus y. And this additive homomorphism, which is what this is called, kind of also applies in ring LWE land with some caveats. So if I add two LWE samples with respect to the same A, then I get this as if I added the secrets, right? And I obtain a new error term E prime. Similarly, I can multiply. I can take g to the a to the power of b, or I can take g to the b to the power of a. And again, the same thing applies to ring LWE. You can just kind of like push through the arithmetic and you will see that it roughly works out. And then the Diffie-Hellman assumption, that g to the a, g to the b, g to the ab is indistinguishable from g to the a, g to the b, and some uniform element, essentially boils down to an equivalent assumption that follows from the LW assumption. So all this is here to say that it really kind of seems rather confusing that we can't just kind of take this scheme that we have sketched based on Diffie-Hellman and translate it to ring LWE. And indeed, it just works out. If you just look at the arithmetic, then it more or less works out. So what I've done here on the left-hand side, I've reproduced the slide that we had previously, and on the right-hand side, I've mechanically replaced everything by the ring LWE formulation. So, think of the right-hand side as taking logs of the left-hand side, so multiplications become additions and exponentiation become multiplications. Right, so we hash our element into the ring, h of x, and then we blind it with a times r, but we now need to add a small error term. Again, the server multiplies by k. On the left-hand side, it took it to the power of k. And this thing is only secure if we add a small error term. So here denoted e prime and e double prime. And then in the end, what we have is on the left-hand side, we kind of do a simple division. On the right-hand side, we do a subtraction. However, and here's one of the caveats, is because we're adding these small error terms, then the lower order bits, so to speak, of the answer will not be correct. So what we're going to do instead, this is a convoluted way of writing this, is to say like we're going to take the most significant bit of this, right? So I'm going to take out this ring and I'm only going to look at the most significant bits. And the reason for this is that the most significant bits will be similar to h of x times k, which is then our PRF evaluation. So let's talk about what the trouble is. So there's essentially three problems with this approach. If you look at the previous construction, what the server needs to do, it receives some CX from the client and it needs to multiply this by k and add a small error term, right? And so if this CX is exactly formed as the client is supposed to behave, then this is fine. But for an arbitrary element CX, this is not safe at all. In particular, if you are prepared to multiply your k by anything I send you and adding a small error, then I can learn k in one shot. So this is really not secure. So because I can maliciously craft a CX. And so what we need to do is we need to prove to the server that the CX that we're submitting is actually of the correct form. But we have to do this in a way that we're not revealing R and E, because that would then allow the server to kind of figure out what h of x was, which would allow the server to potentially figure out what x was, right? Which is what we're trying to hide here. So we need to prove that in zero knowledge. And this can be quite expensive. So the first work that kind of essentially kind of executed and implemented this blueprint from 21, this was ridiculously expensive, right? So the proofs themselves took 128 gigabytes. So this is not a typo. But now with progress in zero-knowledge proof systems, this is down to something like 63 kilobytes, right? But again, we're talking about kilobytes here, not bytes. So this is still a lot more expensive than a Diffie-Hellman kind of setting would be. The second problem is that the client effectively learns E times K plus E prime minus E double prime times R, right? So what we end up with is at the end, we need to round off the lower order terms because they're kind of garbled a little bit. But here we are noticing, well, they're not really garbled because they actually are functions kind of like in the key K that the server would like to protect, and inputs that the client chooses, right? In particular, the client chooses E and R. So it can maliciously choose these in order to learn information about K. So what we have to do here is we have to add this kind of E prime term that is significantly larger than E times K and E double R. So what we have is an expression that h of x is K. And then we have this orange terms here, which indicates that these are all small. Like in this expression, the client has picked E and the client has picked R. The server picked K, which is static, and he wants to protect, and it picks E prime and E double prime. And what we need to prevent is that this expression leaks information about K or equivalent about E prime or E double prime. So the way we do this is that we make E prime a lot bigger. And then we can show using statistical arguments that this leaks very little information about K and E double prime, and we are fine. But what we need to do, we need to pick our modulus Q much bigger than E prime because we want this thing to be correct, right? These terms, these orange terms are meant to be small relative to Q. And in turn, it is the ratio of the noise, and Q is, you can call it the signal to noise ratio, and that means we need to make it big, right? And so in particular, that is the ratio of the initial input, not the ratio with E prime. And if you have a big signal to noise ratio, then solving LW is easier. And the way you control for this, how you account for this, is by increasing the dimension. And the eventual bandwidth is essentially determined by n log Q. So we need to have a big Q that only grows the bandwidth logarithmically, so that's fine, but we need to increase n, and increasing n makes the whole thing more expensive, right? So this is another reason why this thing is not very efficient. And then there's another problem, and that is we somewhat kind of like loosely said that, well, this is roughly, like the expression boils down to roughly h of x times k, right? But what we have is only roughly, right? But what we need to extract correct information in the end. So we have this expression here where we're adding the small error term, and we want to make sure that this doesn't affect the most significant bits, right? We want that kind of those are with very high probability always the same. And the way you can think about this, you can think of the numbers mod q as essentially on a circle where q is 0. And then if we're in the right part of the values, then we're fine, right? We will round to, if we push this with the error around, then we won't end up in a different value. But if we are kind of near this boundary, the rounding boundary, then if the noise pushes things slightly higher, then suddenly it rounds to 0 instead of 1. So that's the main problem. And so what's the solution to this? You make the red area so small that this doesn't happen with very high probability, and that means you need to make Q very big. So you need to make the super polynomial big. And again, this increases signal to noise ratio, and this again requires us to increase n. Okay, so these were 3 problems that you have to tackle when you just want to take this blueprint and lift it to a lattice setting. So all in all, here's like some works, some of them by us, some of them by others, on essentially realizations of this blueprint, right? And as I mentioned earlier, in the kind of very first construction, it was ridiculously expensive. It was a proof of feasibility. And then subsequent work from last year has like significantly reduced this. right? But whereas in a Diffie-Hellman setting, you're looking at sizes of a few bytes. Here you're looking at 200 kilobytes. And the Q in the table means like we're restricting this to up to 2 to the 32 evaluations because some statistical arguments require that. So this means now you can have post-quantum oblivious PRFs, right? You can technically send around 200 kilobytes, but it is quite a performance penalty compared to the pre-quantum setting. I want to close by stepping out of the blueprint, right? So what I started with is to say like, well, maybe LWE is a little bit like Diffie-Hellman. We have oblivious PRFs from Diffie-Hellman. So why don't we take this blueprint and lift it to the lattice settings, right? And then we talked about how this actually has performance penalties that are non-trivial. I also mentioned, well, we can have fully homomorphic encryption from lattices. So lattices give us a way of computing on ciphertexts. So a natural way of realizing an oblivious PRF is to encrypt the PRF evaluation. So what we do is we take an FHE scheme, which would be based on lattices and which can be made post-quantum secure, and we just encrypt our input X. And then given that we can run programs homomorphically, what the server does, it simply runs the PRF, the function f, using the plaintext key k and the ciphertext of that encrypts the input X to obtain an encryption of the evaluation of the function under the key k on the input k. And the client then simply decrypts the FHE ciphertext. So one problem that we have here to make all of this concretely efficient again is in order to have a secure pseudorandom function, you actually need deep circuits. So you need to have like, long chains. And you need something like log lambda. So you need depth roughly 10, right? And so that is, of course, expensive because think of that each level really kind of adds significant overhead in an FHE evaluation. And one thing you can do is to use a very nice idea called the crypto dark matter weak PRF candidate. And here the idea is that you're mixing different moduli, right? And so in its simple form, this kind of PRF candidate, what it says is like, so we pick A, which is a matrix now, mod 2, and that is our secret key. And then we have some input X, which is for now, consider this as a random value, also mod 2. And so we just multiply, we do matrix vector multiplication mod 2, and then we take the result, interpret as a result mod 3, and just add it up mod 3, right? It's as simple as that. And it turns out this modulus mixing technique can be implemented quite efficiently using some FHE schemes. And if you put everything together, then you get something that is indeed more efficient. And so in particular on this slide, I'm comparing this approach, right? So AG24 was like our previous OPRF, like following the blueprint, and then the ADDG24 is again our construction, but now using this FHE kind of technique. And as you can see, you can get, if you don't care about the verifiability of the OPRF, you can make the online cost 10 kilobytes instead of 200 kilobytes at the cost of an offline cost. So you have to once submit 2.5 megabytes. So that might be a trade-off that is not kind of very interesting. But this highlights that maybe when we want to build post-quantum pets, taking the pre-quantum constructions and trying to lift them to a post-quantum setting isn't the most efficient strategy, right? Maybe we need to think more creatively about how to accomplish this. And with that, thank you very much. I left the references to kind of the papers that kind of like we contributed to this space on the slide. Thank you for your attention.